everyone. Welcome to Thieme WebCheminar on dual catalysis today. Dated in Shanghai, journal acquisition publisher of Thieme Chemistry, and I'm based in Shanghai, China. Thank you for joining us today. Before we start, here are a few tips. Webinar is being recorded, and the link of recording will be sent to you shortly after the seminar if you signed up. The second, you will be kept on mute during the seminar, while please feel free to ask questions using the chat window. Questions will be answered as many as possible. If you have any feedback or suggestions, please do not hesitate to let us know by tweet our Thieme Chemistry. I also encourage you to subscribe to our Cheminar series, as well as our newsletter to keep the Thieme Chemistry information up to date. And here I would also like to briefly introduce our journals and some updates. Thieme is a German company with an international presence and over 130 years of experience in publishing science and medical information. Thieme Chemistry products, you may already know some reputed journals such as Synthesis, Synfax, Organic Materials, and Thiopen. And we have also e-products like Synthesis, Science of Synthesis, Pharmaceutical Substances. And in particular, Thiopen, and a gold open access journal, had just received its first impact factor last year. And we also expand the scope of our portfolio to material science and other scientific fields. Last year, we launched a new journal called Sustainability and Circularity Now. It is an interdisciplinary journal focused on sustainability issues. And we have Professor Chris Slutweg from Amsterdam as the editor-in-chief. We have also a product called Pharmaceutical Substances, which should be very useful for scientists working on pharmaceutical development. And next Thieme WebCheminar will take place on September 3rd this year, and the topic will be about soluble graphene nanoarchitectures. So if you have interest, please sign up to this webinar. Let's go back to our webinar today. So we are very happy to have Professor Min Joo as chair of today's webinar. So I will give a short introduction of Professor Min Joo. She completed her undergraduate and master's studies at Seoul National University in South Korea. And then she pursued her PhD at Princeton University and subsequently performed postdoctoral research at Columbia University in the USA. Following her postdoctoral work, she held a position as a process chemist at Eli Lilly and Company in Indiana, USA. And then she went to the academia starting in 2013. 10 years ago, she joined the faculty at Busan National University in South Korea, where she got promoted to be full professor in 2022. In March 2023, she transitioned to the Department of Chemistry at Korea University in South Korea. And since January 2023, she has served as an associate editor for Synthesis, the journal from Thieme. So now I will hand over to Jung.
Thanks, Xiao. Thank you very much for your kind introduction. Okay, let me share my screen and everything is okay. All right, so let me briefly talk about a little bit more about our journal Synthesis, and then I will introduce the first speaker. So Synthesis, as you know, is a reliable platform for publishing organic chemistry papers since 1969. Led by our chief, Professor Mark Lotens, the Synthesis has our editorial team is composed of chemists with diverse backgrounds. So Synthesis is very special in a way that they are very generous to support in-person editorial meeting every year. So last year, we talked about the possibility of organizing special issue on dual catalysis, which is obviously an emerging field in organic chemistry. In that regard, I would like to thank Professor Li Zhugong. And Professor Li Zhugong, as you know, is an expert in the field of dual catalysis, and he has been tremendously helpful to organizing the special issue and today's webinar, including inviting today's speakers, excellent experts in the field of dual catalysis. So last year, we started to collect papers on dual catalysis, and we are very lucky to have Professor Sarah Yunmi Lee at Yonsei University in Korea and Professor Gavin Chichui at University of Hong Kong Science and Technology. And then they've been very, very helpful to invite all these excellent speakers and then publish paper. So please check out the already published papers in this link or in this QR code. To celebrate the special issue on dual catalysis, before moving on, I would like to briefly highlight a few works from the special issue. So we have a great short reviews on relay catalysis and synergistic catalysis. And we also have many research articles, including Professor Ju Hyung Kim's paper on metal-metal relay catalysis. We are also planning of several upcoming special issues. So to celebrate Professor Illar's 80th birthday, we have been working on the special issue. And we also recently started to initiate a couple of special issues, including carbon-sulfur bond forming reactions and water in organic reaction. So if you are interested in these topics, please don't hesitate to contact me or the editorial office. With that, I would like to move on and then finally introduce Professor Wei Ji. Professor Wei Ji received a BS at Lanzhou University in 2006 and then later obtained a PhD degree at SIOC under the supervision of Professor Da-Wei Ma. After that, he moved to US to work with Professor Tin Tost and then came back to China in 2016. He has been working on asymmetric catalysis and natural product synthesis at Nankai University. And then today he's gonna present synergistic catalysis enabled stereodivergent CsP3 coupling reaction. Professor Ji, are you ready?
Can you say it? Yeah.
Yeah.
Oh, okay. Okay. Thank you very much. Thank you, Inshao and Professor Min Joo for the kind of introduction on myself. And I think this is a special turn for the dual catalysis. I think a lot of, as shared by the Professor Jung, a lot of groups in this field have contributed a lot of works from different aspects of the in this field. So today is really my great pleasure to share some story on my own in the field. So my topic is synergistic catalysis enabled stereodivergent coupling reactions. So at the very beginning, I will spend a little bit of time to talk about the background of CC coupling reactions. I think there will be a lot of transformations can achieve the cysteine bond formation. So there will be the synergistic couplings and using the hydrogen for the reductive couplings and using the oxidation couplings of a true CH bond. So today I will talk about the CH coupling between a 1,3-diene or allenes with carbon nucleophiles. So this kind of transformation is 100 alternate economy because this is a formal addition reactions, and you don't need to pre-function the substrate, and you don't need to the oxidant, and you don't need the reductant. So this reaction is a redox neutral. It can be occurred even without a strong base. So it's usually occurred under very mild conditions. So it had a very good functionality tolerance. So during the past 2 decades, a lot of groups have contributed a lot of works in this field. So they are using different transmitters such as the palladium and the rhodium and the nickel For example, the 1-Pelion, the BN-Chost has reported pluralhydride catalyze the coupling of the 1,3-diene with the carbon nucleophores, and then literally Luo and John and Maxson has also reported such kind of retransversion by using the palladium. And for the rhodium, Brett and Widon and Meek also performed a lot of excellent works. And for the nickel system, Qilin Zhou, also my colleague from Nankai University, and Mazit has did a lot of beautiful works. So today, so my group is working on the just on the palladium system. I will show some result of the previous report in this field and using the palladium, the rhodium, nickel. So you can see when using the single transition method for this transformation, there is no any problem to generate one steric centers. So you can see from these two examples, both product was obtained in very high initial selectivity and a very high yield. So there is no any problem for generate one steric center. But when they extend the system to pro-chiral liquefiers, then it will generate two steric centers, and the diastereotypy selectivity is very poor. Yeah, so that means that for the single transition metal catalysis, it is sometimes a problem to control the stereochemistry from the nucleophilic side. So, but there will be some successful examples. For example, in Choster, the paper in 2011, they have, after some optimization of the reaction conditions, solvent, and they find a condition to obtain the trans product with a very high diastereotypy. So using the plate hydrate system, but you can see this reaction can extend to prepare the cis product. However, the cis product is a more desired product, stereoisomers in nature product, such as in the neptosine. So Choster's method can be applied to synthesize this kind of nature product. So I have given an even higher standard for the cis coupling reactions. That means this reaction must to give very high diastereotypy and higher EE, and at the same time, all of the stereoisomers can be selective to obtain with high stereo control. That means that the reaction must be run in a stereo-diverted fashion. So regarding to the stereo-diverted synthesis, there is a very milestone work. I think milestone work in 2013. It was reported by Eric Carrera. So he used the uridyl allylic substitution reaction together with amine system. So these two catalysts combined together with each other, and then to control both the stereochemistry of the electrophiles and the nucleophiles. So to this end, it can be run the reaction in a stereo-diverted fashion. So that's to say that all the four stereoisomers can be obtained with very high initial selectivity and DR values. So after these leading works, the Zhang group, the Min Joo group from Shanghai Jiaotong University, and Chunjiang Wang, I think he will talk his work lately, and the Hartwig and the Fong and a lot of other groups has contributed a lot of works in the field. They're using the uridyl systems together with a larger catalyst compilation, and using allylic alcohol derivatives as a substrate for the stereo-divergent synthesis. And naturally, other systems, including the ocular catalyst NHC together with the copper, the NHC together with the rhodium developed by the Gong group, Liu Zhu Gong group, and the nickel copper bimetallic system developed by Go group also have achieved a very good achievement. So my group is working on using the palladium. So we want to using the palladium catalyze the hydrophorylation of the 1,3-diene or leans together with a second catalyst activation mode, and then to achieve the stereo-divergent carbon-carbon-3 coupling reactions. So our idea is very simple. So at the very beginning, we have to choose the nucleophile activation mode, which is compatible with the palladium hydride system. So we first choose the administer this substrate to test our idea. So this substrate can be activated by a cationic copper Lewis acid and to form a copper as a methyl unit. Wang will talk more details about this intermediate later. And I think this species has been well studied by Wang and Min Joo in some dual catalysis. So my group also have investigated the structure of this intermediate by a DFT calculation, and we found that the isopropyl group here can perfectly share the C phase of this unit, the C phase of unit, and they make the re phase vacant. So it will be it will be perfect mode to accept the addition from the C phase, and then to make a very good control towards the nucleophile site. So then with this idea, we just thinking this reaction. We try the reaction of the 1,3-diene with the administer using the palladium and the copper dual catalysis. Because the reaction is a formal addition reaction, so in principle, it will no need any additives such as acid or base. So first, in the absence of any additives, we mix these four together and we can get any desired product. So that means that we think even the copper was used to activate the substrate here, and by correlation, the proton here is still less acidic to be deprotonated. So we need a base to help the deprotylation process. So then we have tried the plasma carbonate, and we also didn't get any desired product. We have also tried other bases such as the sodium carbonate and the more strong base plasma butyl oxide and organic base DBU or pyridine. By using these bases, we failed to get any desired product. So what's the problem? So we think this base is okay. It's basically enough to deprotonate the proton here. So there will be no problem to generate the nucleophiles. So the problem comes from the generation of the pi the electrophiles. We know that the formation of the palladium hydride, we need an acidic condition to facilitate the oxidation of the oxidation to generate the palladium hydride. So under such strong base conditions, the formation of the palladium hydride will be prohibited. So then we have to use a more weak base. So the triethylamine is a very good base for this system. When we switch into this base, and we found the reaction between the 1A, the 1,3-diene, and the administer work very well to give the desired product with very high diselectivity and the DR values. So we're using the Josie force for the ligand for palladium and the ferrofox ligand for the copper. And by choosing a proper combination of these two catalysts, these two ligand, we can achieve the stereo divergent coupling. That means that all the four stereoisomers can be obtained with high inertial control. So there is a triple catalytic cycle, because besides the palladium and the copper cycles, there also has a base cycle here. So the reaction was initiated from here. The Lewis acid copper was activated the administer, and under the triethylamine, it was occurred deprotylation to generate the nucleophiles, and then the protonated amine react as a Bronsted acid to react with the palladium, and then it generates the palladium hydride. This species then undergoes a migratory insertion into the 1,3-diene. 1,3-diene to generate the pi palladium species. Finally, the CC bond formation between the electrophile and the nucleophile to resulted in the formation of the CC company product. So the ligand on the copper and the ligand on the palladium separately control the stereochemistry of the nucleophiles and the electrophiles respectively. So to this end, we can get a stereo-divergent coupling. So this is the substrate scope. You can see both the thin selective coupling and the anti-selective coupling can give a very high stereo control. So besides the terminal 1,3 diene, even the internal 1,3 diene is also work for this system in this system. So after the success to coupling the 1,3 diene with the adenine esters, we later move to the alkoxylene aminoline as a substrate, as a coupling substrate. So you can please see the right part of this slide here. So we are using the palladium and the copper system, the biallelic dual system, and using the DTBN-sec for the copper and the ferroflux for using DTBN-sec for the palladium and the ferroflux for the copper, and the coupling between the aminoline and the adenine ester work very well to get the desired product. At the same time, at the meantime, the stereo divergent process can be achieved by using the right combination of the catalyst. So for the coupling of the alkoxylene with the adenine ester, the system is a little bit complicated. So you can see when we want to produce the anti-coupling product, we just using the Al3. This is a Quinox P ligand for the palladium, and using the ferroflux A1, the S-proper substituted A1 as the copper, and then we can successfully to produce the anti-coupling. So at the very beginning, when we want to switch the diester selectivity, we first try to switching the chirality of the ligand on palladium or the chirality on the copper, and to see whether the diester was reversed. And then indeed, we can reverse the diester by such protocols to a moderate level. That means the thin coupling product can be obtained in 5 to 1 diester. But further to improve the diester field, from then we screen different ligands for the system, and then we found that using the L1, the ferroflux, using the L2, the final substitute the ferroflux for both the copper and the palladium, and we can get the thin coupling product as the major isomers, and the diester safety was increased to 10 to 1. And further, a study indicated that replacing the copper to 0 as a nucleic acid to activate this adenine ester, we can further increase the diester to 20 to 1. So by using such complicated dual catalyst systems, we finally achieved the stereo divergent coupling, and both the thin and anti-coupling product can be obtained with a high stereo control. So our method can be applied to total synthesis of lateral product. So the methyl F and the methyl G are two lateral products, two amino alcohol lateral product. So the difference between these two is that for the F, the hydroxy group and amino group is a trans configuration, and for the methyl G, the hydroxy group and the amine group is a cis configuration. So our method, our biometric method, can be used to both the thin and anti cis coupling. So we just use the 1A and 2H as the substrate, and use different bimetallic system. We can obtain both the 2S, 3S, and the 2S, 3R coupling product in moderate to good diester safety and good inertial sensitivity. Then using the same procedure to transfer the functionality to after some functional transformation, we found to finish the total synthesis of these two lateral product. So from here you can see we use one common method to synthesize two diastereomeric lateral product. So after succeed in the adenine ester as a liquefier, we then move to the aldehyde. So we think the aldehyde can be activated with by amine to generate the enamine. So we think maybe we can combine this reaction mode together with the planar hydride. So this is the catalytic cycle. So starting here, So under acidic condition, the amine can activate the aldehyde to generate the enamine. So this is the nucleophile. And then at the same time, this is an acidic condition, the planar hydride formation, and then occur migratory insertion into 1,3-diene to generate the pi palladium to generate the electrophile. Then the CC bond formation between these two species, then we can get the final product. So this is the idea. So at the very beginning, we think this reaction might be a very simple reaction because we need an acidic condition, and the acidic condition can facilitate the formation for the enamine, and also can facilitate the formation of the palladium hydride. So there will be no any problem for the compatibility of the two catalysts. But when we tried many ligands, electro-rich ligand, because electro-rich ligand can facilitate the formation of palladium hydride, we failed to get any desired product. So we think the problem may come from the CC bond formation because the enamine is a relatively weak nucleophile. So the energy barrier for the CC bond formation between the enamine and the palladium may be high. So to accelerate this step, we need a more reactive, more electrophilic palladium species. So then we think we can using an electrodeficient ligand for the palladium. So we choose the phosphoramidite. So this ligand is very electrodeficient. So under the L7 and L8, together with the hydroxy amine alkyl catalyst, we can achieve the coupling of the 1,3-diene with the aldehyde. And then by using a different combination of the chirality, we can achieve both the 4 stereoisomers with a high steric control and a high yield. So this is a selected example of the subscope. So this reaction has a very wide subscope. So besides the 1,3-diene, we can even extend the substrate to 1,3,5-triene and 1,3,5,7 conjugate tetraalkenes. So without a modification of the optimal reaction conditions, the desired product can be obtained. Both the same and the anti-selective product can be obtained with 99% EE and 20 to 1% DR, or more than 10 to 1%. And the radioselectivity very good, only occurred at the terminal alkene here. So then we move our attention to the ester. Ester is the more stable nucleophiles compared to aldehydes. So Slater and Smith and Weiss have developed a lot of carbon-1 ammonia chemistry for the PFP ester. They're using the BTN catalyst to activate the PFP ester to generate this enolate. So we borrow this chemistry and to introduce it into the palladium hydride system. And we think maybe we can using the combination of the BTN and the palladium to achieve the stereo direct coupling of the PFP ester with the 1,3-diene. So this is our idea. So the result is that the DTBN SEC1 or the DTBN bifurp is the ideal ligand for the palladium for this system, and together with the commercial available BTN catalyst, the azo or the benzo substrate BTN is here. So the coupling work very well. Both the syn and the anti-coupling product can be obtained with good steric control. So then we're using this method to synthesize bioactive compound, the tapentadol. Tapentadol is a pain relief drug used all over the world. So starting from the 1,3-diene 1A and the line, the PFP ester line. So using the palladium 2, the R configuration palladium 2 and the R configuration BTN catalyst. So the coupling can be obtained in the grand scale to get the product in 98% yield with 8 to 1% DR, and the EE is beyond 99. So after some further transformation of the functionalities, we finally can obtain the tapentadol in a very short route, in a symmetric route. So then we also tried the coupling of the PFP ester with the alkoxylene. So this reaction is very simple. We just found that this ligand, the BiBOP, which were developed by Min Joo in SLOC. So we cooperate with each other and develop this method for the company of one alkoxylene, so PFP ester, to get this product. So this product is a beta hydroxyamide. So it's also a very useful sensor in organic synthesis. So besides company product, because the PFP ester is very useful functionality, can be transferred to many other groups. For example, we can transfer it to the amide, and then we using a lead for acetate for a Hofmann rearrangement. Then we can transfer the product 8 to this product. This product is a beta amino alcohols. So by using the coupling reactions together with the rearrangement procedures, you can get a stereo divergent synthesis of beta amino alcohols. So both the 4 stereoisomers can be obtained. So this is also a very useful method in organic synthesis, because the beta amino alcohol is very useful sensor for ligand and for oxide catalyst. So far, we have achieved the stereo divergent coupling by using the admin ester and the aldehyde and the PFP ester. So both of these 3 belongs to non-stabilized liquefiers. That means that without a catalyst, without activation by a catalyst, the aldehyde or the ester itself can't react with the electrophile. That means that there will be no background reaction in such dual catalytic system. But for stabilized liquefiers, so it can be easily deprotonated by a very weak base, or even in a neutral conditions, it can be deprotonated. So the background reaction will occur. So that means that for stabilized liquefiers, it will be a very challenge to prohibit the background reaction. There will be some single catalysis pathway occur in the system, so which make it very difficult to achieve stereo divergent coupling. So you can see I have showed an example here, just in the bottom. So when Min Joo have tried a reaction of the oxyindole. Oxyindole is a very typical stabilized liquefiers. Because it easily to isomerize for the inophone. So he have tried bimetallic using the copper and iridium, the bimetallic system for the city bond formation. They have obtained the same product using this system, because the same product is the inherent biased diastereoisomers. So this product was obtained in very high stereo control. The DI is 20:1 and the EE is 99. So when they try to reverse the diastereotivity, so reverse the stereo control at the alpha position or the beta position by switching the chirality of the ligand on the palladium or the chirality of ligand on the iridium, they failed to reverse the diastereotivity. That means using for the challenge stabilized liquefiers is sometimes very difficult to achieve the diastereotic synthesis. So how to solve this problem? So we think we can using a two-phase system to solve this problem, because the base was in the aqueous system, so it can't meet with directly with the nucleophile, so it can't play the role of a base to deprotonation of the nucleophile. So it can be entered the organic phase only when it was formed a tight ion pair with a positive phase transfer catalyst. Then it can react with liquefier to generate this ion pair, and then react with electrophile. So under such biphasic systems, the single catalyst pathway was restrained, and the synergistic catalysis pathway was promoted. Then this gave our ability to pursue the stereo divergent synthesis. So after using the 1,3-diene and oxyindole as a model substrate to investigate this system, so reaction started here. So the base was in the aqueous phase. It was transferred by the transfer catalyst to the organic phase, and then it reacted with the uniform for 1A and to deprotonated to generate the tight ion pair A and generate the acetic acid, which was reacted with the palladium and to generate the palladium hydride. And the palladium hydride reacted with the 1,3-diene to generate the palladium electrophiles. So there is a CC bond formation between the species A or B and C and generate the final product 3AA. So this is a catalytic cycle. And so in the case we have found that the bisphosphite ligand is okay for the palladium, and for the syn selective coupling, we have to use in the ammonia, the amino alcohol derived phosphonyl phase transfer catalyst. And for the anti-selective coupling product, we have to use in the quinidine or the quinine derived tetraammonium phase transfer catalyst. So here we have to give a more close attention to the stereo control. So you can see here. So for these two product, this is the syn selective, this is the anti-selective. The difference between these two products is the configuration at the beta position here. So here for this product, the beta position here is the beta R configuration, and this product is beta S configuration. But for this product, we're using L6 for the palladium, and for this product, we're using L7 palladium. So you can see the structure of the L6 and L7. The only difference is just the substitution group on the aromatic ring on the R group here. So the chirality of the L6 and the L7, including the backbone of the axial chirality and here, the link binary are the same. So that means that we using the same sense of the ligand, same sense of configuration ligand, but produce different, the absolutely different stereochemistry at a beta position. But so generally in our previous reported systems, such as in the copper and the plate system, we say that the stereochemistry as a electrophile as a palladium palladium is controlled by the ligand of the palladium. But here in this system, we can see the stereochemistry at the beta position is not independently controlled by the palladium. It must controlled by the palladium and the PTC, the phase transfer catalyst, cooperatively. So that can explain the stereochemistry result here, shown here. So with this, we have to modify the catalytic cycle. So we think the formation of the palladium is a reversible. That means the palladium and the palladium migratory insertion 1,3-diene is a reversible. So there will be an equilibrium between these two species, this palladium and this palladium. And then the CC bond formation between the A and these two species is determined by the reaction energy barrier. So controlled by the chirality of the phase transfer and the ligand on the palladium, it cooperatively controlled the two steric centers of the phase transfer and the steric center on the analytic side. So that means that the CC bond formation step is the rate determining step. It also the relation determining and the diastero selective determining step. So this system is quite different as our previous report systems, because this system, the two catalysts separate control or partially separate control the stereochemistry. But in this system, the two catalysts cooperate to control the two new stereo centers. So to close my talk, so we have developed a different combination with the palladium catalyst with a nucleophile activation catalyst. So using the synergistic catalyst system, we have achieved a stereo-divergent coupling of 1,3-diene, including aldenes with different carbon liquephiles such as adenine ester and aldehyde and PFP ester and oxyindoles. So just early this year, we have submitted a personal review for our works. You can see more details of all this chemistry in this paper. So So finally, I should like to give some thanks to my co-workers and the foundings. So Qinglong Zhang is the first person in my group to work in this field, and then Huimin Yu and Wei Cai and Min Joo and Min Huizhi and Jin Qianghan have joined to this field in my group. And also I have to thank the foundings from the Nature Science Foundation of China and Nankai University for the funding support. And also I have to thank all of you for your kind attention, and it's my pleasure to answer any questions from you. Thank you.
Thank you so much, Professor Wei Ji. So I think Professor Ji can receive 1 or 2 questions. So in the meantime, while we are waiting for the questions from audience, can I ask 1 or 2 questions? So in one of yours, so it's beautiful that you can control the stereogenic centers in a stereodivergent manner. So it's all, to me, it's like almost magic. Yeah. So, but in the middle of your presentation, you showed a substrate like beyond the diene system, so you can test a triene or tetraene, and then you didn't have many issues, like in terms of regio selectivity.
Yeah. So I will show you here. Yeah, for the regio selectivity. For the aldehyde system, I see. Yeah, this side.
Right.
Yeah. So I should say that for the first comparing the internal 1,3-diene and the terminal 1,3-diene. So the internal 1,3-diene is less reactive in this system comparing to the terminal 1,3-diene. So that means if this is a terminal arcing here, this substrate is more reactive. So when we for the triene, so the first reaction just at this position, so the regio selectivity is very good, because this steric here is there will be less steric here, so the cis bond formation was generated here. So that's the reason. So we also didn't observe any only over phosphorylation product. That means there was no second addition here. So because the steric here is very bulk here, so the second reaction is completely prohibited. So both the regio selectivity and the chemical selectivity is very good for the triene and the tetraalkenes.
Okay, thank you so much. Do we have any other question? The audience can also use the chat window after his presentation. So if you have any further question, please use the chat window to ask questions to Professor Ji. And with that, I would like to thank Professor Wei Ji once again for the wonderful talk, and then I will move on to the next speaker.
Okay, thank you much.
Thank you.
I stop sharing.
All right. So the second speaker is Professor Philip Chen. So to briefly introduce his academic background, Professor Philip Chen received BS at University of Bristol in 1995, and then later received a PhD degree at University of Oxford under the guidance of Professor Mark Maloney. After some postdoctoral work, he eventually started his independent work at Nanyang Technological University in Singapore, and moved to Australia in 2014 to take a professor position at Monash University. He's been working on homogeneous catalysis, reaction discovery, functional materials, and natural product synthesis. So today he's gonna talk about recent adventures at the intersection of branched acid, gold, and photoredox catalysis. Professor Chan, are you ready?
Yes, thank you. I will now share my slide, hopefully. Can everybody see my slide okay?
Yep, perfect.
Excellent. Thank you. And I will also use a laser pointer. Okay, I'd like to begin by thanking Professor Min Joo for that very kind introduction. And I would also like to thank her and Professor Lu Zigong for the very kind invitation to come and onto this webinar to present some of our work in dual catalysis. I've titled my talk Recent Adventures at the Intersection of Bronzed Acid, Gold, and Photoredox Catalysis, because I'd like to show you some of those combinations of those three different catalytic systems and how we were able to make them work for some of the chemistry that we were trying to achieve. Before I do that, though, what I would like to do is just maybe share with you where Monash University, as Professor Jung mentioned, we're located in Australia, which is true. Monash University might not come instantly to your mind as to where it is in Australia. So we're located in the state of Victoria, which is here. And in particular, we're located in Melbourne. So this is where we are. I'd like to begin also my scientific presentation by making a bit of a confession. We're really honored to be given this opportunity to present some of our work in dual catalysis. This is work that we've only recently started doing in our group, so really only in the last 5 or 6 years. And so to be given this opportunity at such a very early stage in our contribution to this field is it's a real honor to do so. And I also get a bit of imposter syndrome, as if you will, by presenting particularly some of the work that Professor Wei has just presented. What I'd like to do in today's presentation of our work is to give you 2 stories of some of the work that we've done in dual catalysis. The first one, as you can see here, combines chiral gold 1 catalysis with bronzed acid catalysis. And in doing that, what I'd like to tell you is a bit of a background story as to how we got to where we got to here on this slide, where we took propagylic alcohols of this type here with a beta amine functionality at the side, and how we were able then to use essentially a chiral gold catalyst here. But chiral gold, essentially in as much as that it's an achiral gold catalytic system, but what it releases in hidden view is a chiral bronzed acid, the chiral counterion, giving us that chiral bronzed acid. And in doing so, what we were able to do, and so I need to get rid of the pane here because I can't see all of my slides. I don't know how I'm going to do that, but maybe please pardon me for a second. I'll just get rid of that. And okay, that's better. Sorry about that. So I couldn't see all of my slide there. So by doing that and using the phosphoric acid counterion, the counterion derived from the phosphoric acid, we were able to access asymmetrically the pyrrole 2-al methanols shown here in yields up to 99% and ERs of 91 to 9. On the other hand, if we switch the counterion to a more stronger hidden bronzed acid, here is the one that's shown here, and the name escapes me the name of this bronzed acid, but nonetheless the more stronger bronzed acid that is released as this counterion is quenched by a proton in solution, we were able to show that you were able to access these indene fused pyrroles shown here in 98% up to 98% yield and 99 to 1 ER. And so, as I mentioned, this work actually started from our interest in bronzed acid catalysis, and this is a work that we completed a few years ago now, where we were really interested in looking at dehydrative Nazarov type electrocyclizations. this is an area of chemistry that's extremely well known in terms of the Nazarov cyclization, but in the dehydrative space, where you lose a molecule of water to form the carbocation in situ, not much of that was known in terms of its enhancer selectivity. The reaction itself has been known since the 1960s, but an asymmetric version was not known. And so we had an idea where we thought if we could take advantage of hydrogen bonding interactions that were provided by this amine group here, this tosyl amine group in most cases, through hydrogen bonding with our Bronsted acid, the conjugate base of our Bronsted acid, and at the same time we can also exploit ion pair assisted ion pair interactions as shown here. Maybe when this molecule undergoes the 4-pi electrocyclization, we can control how it does that and enhance it selectively to get us to our product as you can see here, this indene product. And this worked extremely well. We were able to get yields up to 99% and also EE values up to 99% as well. And it was actually during this study that an idea occurred to us. So as most methodologists would do, we would go through a substrate scope, and we showed that this reaction was applicable for a variety of probobulic and aryl alcohols. But going back to the probobulic alcohols, we saw an opportunity, and this opportunity actually came from our interest in gold catalysis. And that is, as you can see here, this amine group that we used for hydrogen bonding, we thought that we could further react this in a hydroamination reaction with the remaining probobulic group shown here. And as you can see, we can access a variety of substituted alkynes shown here in good yields and EE values. And so with that in mind, that was the first thing that we looked at. And so in a follow-up paper that year, we felt that maybe we could use an acid, and in the presence of our gold catalyst, maybe we can get to these products directly without having to form that alkyne product, as you saw previously on that previous slide. And indeed, we're very happy to see that that was the case. And we were able to access a variety of indenes fused pyrrole products, as you can see here. In most cases, in very good yields, typically in the high 70s up to almost quantitative, and also with good EE values, as you can see on this slide. Mechanistically, what we thought was happening was we were essentially lending some of that chemistry that we had developed earlier on in our Bronsted acid catalysis. And as much as that, we took our Bronsted acid, shown here, our chiral Bronsted acid, that Bronsted acid would protonate our alcohol. That in turn would affect dehydration. So we would get rid of a molecule of water, and we form this allylic cation shown here. In this allylic cation, we might anticipate the negative charge that's sitting on our amine here, our triplamide, to undergo ion pair interactions with our carbocation center here. So here's our intimate ion pair species. And at the same time, the PO double bond would undergo hydrogen bonding interactions with our amine as well. And so we would have our hydrogen bonded ion pair assisted transition state here that would then undergo topo selectivity, of course, a term that was first coined by Ken Hook at UCLA. And in doing so, we would then set the chiral center here. And once we were able to do that, our gold catalyst would now come in, like so. It would, of course, activate our alkyne. So we would take advantage of the alkynophilicity of our gold 1 catalyst. So this would activate our alkyne motif here to become susceptible to hydroamination with our amine group here at this position. And through that, we would undergo hydroamination, protodeoration to get to our Indian fused pyrrole product shown here. And so with that, we thought, well, you know what, that is nice, but it's still two separate catalytic systems. Can we make this reaction a little bit more elegant, I should say, not eloquent, elegant. And one thing that sprung to mind was the use of a chiral counterion. I do apologize, I should have maybe put in one of the earlier works with this system. This is a concept, of course, that was not developed in my group, but developed by the groups of Tost and Echevarren, for example. And so the idea was very simple. So what we wanted to do was maybe generate that Bronsted acid in situ from a chiral counterion to our gold 1 catalyst. And one of the first things that we thought about was this system shown here, where we believe that we could indeed generate our Bronsted acid once this counterion leaves our gold 1 catalyst when it's introduced into our reaction mixture to reveal our Bronsted acid. And when we did that, again, we were able to show one example here that indeed we were able to generate this as in principle as one catalyst, but in reality what was happening is that the Bronsted acid was being generated in solution from our chiral counterion. It then affected the dehydrated Nasaroff reaction, and then our triphenyl phosphine gold 1 complex would then come in to do the hydroamination. What we subsequently found as well is that when we switched over to this less acidic counterion, so this is the phosphoric acid, a different reaction pathway opened up instead. And instead of the dehydrated Nasaroff cyclization, what we saw in this instance was a hydroamination reaction occurring first due to our gold 1 complex, and then this was followed by a 1,3-allylic alcohol isomerization to give us these pyrrole substituted methanol products shown here in good yields and up to 91 to 9 ER. And we were pleased to show that in the first instance that this reaction was quite general for a variety of substrates. But I need to let you in on a secret here, and that is when we first did this reaction for R equals H, so here it's just a simple phenyl group, we indeed got yields of 99%, but initially we got ER values of greater than 3 to 97. We were really delighted with this result. Unfortunately for us, we ran out of HFIP, which was required in this reaction. And when we did that, we could never ever repeat these ER values consistently. We took the reaction apart. We spent over 7-8 months trying to get this reaction to be consistent, but we could never ever be able to do that. Every now and again, we would repeat those best ER values, but it was only ever now and again. And in reality, we only ever got consistently the lower range of 9 to 91 ER values. And that's where we felt that probably, we don't actually know why that is, but that was probably where the real enhanced selectivity of this reaction sat. So nonetheless, we moved on and we looked at the reaction mechanism, and we thought that with our propygylic alcohol shown here, there were two possible pathways. with our gold catalyst, I do apologize, it's a very small slide here, but with our gold catalyst and the stronger counter ion that would generate the stronger bronze acid, what we thought was that our gold catalyst, or indeed the stronger bronze acid, would protonate our hydroxyl group and in turn dehydrate at this position here. And as a consequence of that, we will form our carbocation species here. Our carbocation species here would then engage in an intimate ion pair interaction with the conjugate base of our acid, and also in hydrogen bonding interactions as well. And that would set it up to a asymmetric 4-pi electrocyclization reaction to give us our indene. And then, of course, in the presence of our gold catalyst, hydroamination would occur to give us, in the first instance, this pyrrole gold species, which would then protodeorate to give us our product shown here. On the other hand, if we use a phosphoric acid as a counter ion, the less acidic phosphoric acid as our counter ion system, what we would first see foremost, because the less acidic phosphoric acid being generated in situ is not capable of dehydrating our alcohol, and instead what would happen is the hydroamination would occur first to form this pyrrole ilium system shown here. And with that, our HFIP now comes in, and it can do one of two things. First and foremost, it can protonate our hydroxyl group, initiate dehydration to give us our carbon-centered cation species here with this intimate ion pair species and hydrogen bonding through the nitrogen, this asophilicity. And with that, we will then get to our product shown here. Alternatively, in the absence of HFIP, this alternative pathway could occur where we get a shuffle, if you will, of our hydroxyl group, which will then, oh, sorry, I should mention here, this is an intermolecular 1,3 allylic alcohol isomerization to give us our products. Alternatively, it can do that through the conjugate base directly to give us our product shown here. What I'd like to do now is maybe switch gear a little bit and just tell you some work we've been working in the photoredox catalysis space with bronze acid catalysis. And this is some work that, again, we finished very recently, which is the Minsky type alkylation of N-heteroarenes via an EDA complex, this EDA complex here, and a chiral bronze acid and light. So in this reaction that we initiated, our inspiration came from two works. The first work was from the Phipps groups at Cambridge University, where they reported this iridium system here in the presence of a bronze acid was able to do this Minsky type alkylation reaction. And hot on the heels of this work, also work from the Shang and Fu group, who showed this sodium iodide and triphenylphosphine system as well that was able to do the same reaction. So in our case, what we were able to show was we were able to initiate this reaction in the absence of a metal of any description, and in actual fact, be able to use an EDA complex. And so we use this photoredox active ester shown here in the presence of the Hansch ester. I do apologize, I forgot to draw the Hansch ester, and one of these two bronze acids. We were able to initiate alkylations of the type, as you can see here through this scope, in relatively good yields, typically above 70%, and up to anywhere in the 90s, and in good EE values as well. So typically in the high 80s to 90s. The substitution patterns, as you can see here, were well tolerated. So our benzylic groups of the type shown here, alkyl groups, as you can see here, heteroarenes, and also including substrates, including a thiol group. We're also able to show that different substitution patterns on the isoquinoline ring worked extremely well as well. And so again, good EEs. There's some moderate EE values here, as you can see, and these were only achieved with these spirocyclic chiral bronze acids, but nonetheless they go what I would like to term as synthetically useful EE values. And then moving away from isoquinolines to quinolines to isoquinolines, we also show that pyridines were also good substrates for this reaction. We also did quite a deep dive as into to the reaction mechanism, and we showed that first and foremost that this should be a radical reaction. So if you use a radical scavenger such as Tempo, you can show that you can shut this reaction down. You don't get any of the products at all if you took this quinoline photoredox active ester, and so there's no product formation, and in actual fact by mass spectrometry you can detect the Tempo derivative shown here. We also showed that the individual substrates on their own, as you can see here, are very much in the UVA region. But when you start mix them together, you see this red shift here. And you can see that visually as well. It goes from slightly pale yellow color to a very noticeable bright yellow color here once you start mixing all the reagents together. And of course, in the UV vis spectrum, you can see that red shift quite clearly. We were also able to show that this is to be the case when we looked at the molar ratios of the redox active ester with our substrate, and once you get to a one-to-one equivalency, you can see a maxima occurring in terms of the absorbance. Likewise, we did a light off, light on reaction. So when the light was off, there was no reaction. But the minute you switched the light on, the blue LED light, you saw product formation. You switched it off again, you saw no reaction. But once you switched it back on again, you saw reactivity and product formation. And then finally, in terms of chirality and how we were introduced chirality, we showed that, as you can see here, when you use a photoredox active ester where there is no site for hydrogen bonding, such as this substrate shown here, there's no secondary nitrogen here for hydrogen bonding. You can get product formation, but there's no EE to go with it under the standard conditions. So mechanistically, what we think is happening is that our photoredox active ester, our Hansch ester, I'm glad to see I've actually drawn it in here, so just HT for short, as you saw in the previous slides. They can come together because of those weak Coulombic interactions. It forms this EDA complex, electron donor complex, electron donor acceptor complex shown here. And so when we expose this EDA complex to our blue LED light, this starts the fragmentation process where we form this nitrogen-centered cation species as well as this carbon-centered species shown here, 3A. This carbon-centered radical species here can further fragment to form the this oxygen-centered species here and the thalidomide anion, and this oxygen-centered radical species here, 4A, can undergo can eliminate carbon dioxide, and when we introduce our substrate, our quinoline substrate in this instance here, 1A, in the presence of an acid, we use if the reaction is chiral, of course, TFA is replaced by our phosphoric acid. We form the radical species from the decarboxylation. Here's our carbon-centered radical, which can now add in to our protonated substrate shown here in this manner, like shown here, to form this radical cation here. This radical cation can react further with another molecule of our photoredox active catalyst, as shown here, and to regenerate our acid. I've written TFA here, but our acid can equally be our chiral bronzed acid, and we regenerate our carbon-centered radical here, this species here, along with this guy here, and this then sets up pathway, which is a radical chain mechanism maybe. Alternatively, another pathway might be, so path B here is just showing the Hanchester essentially going to the fully aromatic pyridine. Alternatively, what could happen here is that we get deprotonation either by our substrate 1A, so it doesn't necessarily need to be our acid protonating our nitrogen center here. It could be protonated by this species, or indeed our thalidomide anion to form thalidomide shown here, and we get our product shown here. We think in the instance where we generate chirality, this is the transition state shown here, where we have our nitrogen center here sitting in an equatorial position, and allows that addition process to occur in this manner from to install the chiral center here at this carbon center, as well as here, of course. And with that, I'd like to finish my presentation. This is a bit of an old slide now, but in particular, what I'd like to do is find Jung, he's since graduated, and Yi Chao. They were one of the main instigators and a lot of the work with the dehydrated Nazarov cyclization, and then that work with gold catalysis to form the dual catalysis reaction pathway. Unfortunately, Jason, who did the photoredox catalysis work, is not here, unfortunately, but he was involved in making that work, realizing that work. And finally, I'd like to thank the Australian Research Council and Monash University for funding, and you for your attention. Thank you.
Thank you, Professor Philip Chen, for the wonderful presentation. So thank you for showing us various possibilities combining two different types of catalysis to achieve the goal. And so now we have one question from the audience. So I think he or she is wondering about whether free radical intermediate actually is formed in your last project, because it looks like a highly acidic condition. So do you have additional evidence for the formation of radical intermediates?
Yes, so maybe I'll go back to my slides. So we're pretty confident some of these control experiments that we've done. So for example, in this experiment here, even though we have the acid, as you can see here, but in the minute we introduce tempo, so tempo is a radical scavenger, so you imagine this part of the molecule here is tempo. When we add this in, there is no reactivity. We don't get product formation. And also, you can see it, the UV vis, that shows that, that shifts it to the blue LED region. But more importantly, is this light on-off reaction. So as you can see here, with time, when you don't have light, there is no reaction. But the minute you switch on light, you get reactivity. So we're really confident that this is a radical reaction rather than an acid catalyzed reaction.
Hey, thank you. So I have a few more questions. So there is a question about whether loop rearrangement occurs in the first reaction of gold catalysis. Can you see the questions or?
Okay, so which first so this
gold catalysis.
Yeah. I think this is just straightforward hydroamination. I think it's just straightforward hydroamination. We've worked on this system for quite a while now. We're pretty confident it's just straightforward hydroamination, a straightforward hydroamination reaction.
I see. So some of your products looks already very interesting to in the industry. So have you ever explored the possibility applying your compounds or your reaction for industrial application?
Yes, we have. Yes, that's a very good question. Yes, we have. That's some work that we have some. Yeah, we have some ongoing work with a company right now.
I see, but it's a secret.
At the moment, yes, I'm afraid so. Unfortunately, I can't share that.
Totally understand. Yeah.
But the answer to that is yes, we do. Yes.
All right. Thank you once again. Thank you so much for the wonderful presentation. So the audience, if you have any further questions, please don't hesitate to use the chat window. With that, I would like to move on to the final speaker. Let me see. Okay, so today's final speaker is Professor Chunjiang Wang at Wuhan University. Professor Wang received a BS at Central South University in 2000, and then received a PhD degree at SIOC after working with Professor Min Joo. Later, he moved to US to work with Professor Sumu Zhang, and then he started his independent career at Wuhan University at 2006, and then he has contributed asymmetric catalysis and development of biologically active chiral molecules. Professor Wang, are you ready? Can you share the...
Okay, can you hear me? Okay.
I can see you, but can you share the screen as
well?
well?
I will share my slides first. Okay.
All right.
Okay, can you see the slides?
Yep.
Okay. First, thanks Professor Zhu's kind introduction, and I want to give my thanks to Professor Zhu and also Professor Gong's kind invite me to attend this seminar. And today's the topic of this seminar and is about the dual catalysis. And in my presentation, and I will report our recent progress and with the methylated azomethane in it. And azomethane in it are nitrogen-based 1,3 dipoles and consisting of an iminium cation and next to kappa anion. And just now, and Professor V.V. Zi have mentioned this intermediate in his talk. And the 1,3 dipole second addition reaction is one of the best methods for the preparation of 5-membered nitrogen hydrocycles. And in the last decade, methylated isomerization units and ligated with chiral ligands were widely used as 1,3 dipoles for the construction of highly functionalized pyrimidine derivatives. And this unit can be formed in situ from aldimine ester with chiral acid and basic condition. And this aldimine ester is readily available via simple condensation between aldehyde and these amino acid esters. And with the methylated isomerization unit as 1,3 dipoles, and many research groups made great contributions in catalytic asymmetric 1,3 dipolar cyclodietion reactions. And next, I will spend a little time to introduce some of our previous work. And with the strategy of synergistic activation, and we designed a chiral ligand named as TF bifenphos. And this chiral ligand exhibited excellent performances in isomerization unit involved 1,3 dipolar cyclodietion reactions, and especially for the preparation of pyrimidine derivatives and bearing a unique tetrasubstituted quaternary steel centers. And later experimental and computational study revealed that the hydrogen bonding interaction between the amino group in the chiral ligand and the electron withdrawing group in the dipolarifier is a key point for enhancing the reactivity and the stereoselectivity control. And we also developed several higher ordered 1,3 dipolar cyclodietion reactions and for the preparation of fused or bridged 6-membered nitrogen heterocycles. And in 2011, we reported a copper-catalyzed asymmetric microaddition reaction of isomerization unit and with actinium bisphosphonate, and followed by acetic hydrolysis and affording a natural alpha amino acid derivatives bearing a geminal bisphosphonate moiety. And to our knowledge, this is the first example of methylated isomerization unit serving as nucleophile instead of 1,3 dipole. And later, the stereocontrollable nucleophilicity of isomerization unit was further demonstrated with various precursors, such as glycine derived aldimine ester, and this alpha substituted aldimine ester, and this is the cyclic imine ester, and also even the less reactive cyclic ketone imine ester. And all these precursors could be employed as stereocontrollable nucleophiles in microaddition or microaddition-initiated cascade reaction for the preparation of unnatural alpha amino acid. And with chiral metal complex and basic condition, and the imine ester could be readily converted to methylated isomerization unit. And this rigid 5-membered ring structure and improved its nucleophilicity and stereoselectivity control. In 2019, we were invited to write a review article entitled Recent Advances in Methylated Isomerization Unit for the Synthesis of Chiral and Natural Alpha Amino Acids. And the synergistic catalysis is a widely used biomimetic strategy in organic synthesis, and employing 2 different catalysts and 2 reactive species are generated simultaneously, and one with a higher HOMO and the other with a lower LOMO, and thus enabling chemical transformations that are impossible or inefficient with mono catalysis. And in last decade, dual metal organic, metal-metal and organic catalytic system have been reported. And for dual metal catalysis, and some challenges need to be mentioned. And firstly, the 2 metal complexes must be compatible, and the ligand exchange and should be avoided, since the ligand exchange can hamper or even shut down the reaction. And secondly, the generation of the 2 reactive species must be comparable to facilitate the desired transformation. And asymmetric monocatalysis has been well developed. However, most transformations do not allow direct access to all possible stereoisomers with more than one stereogenetic center are formed in the reaction. And the dual catalysis provide a potential solution to this challenge. And in 2013, the Carrera group addressed this limitation by introducing the concept of stereodivergent dual catalysis. And in this reaction, and chiral organocatalysis controls the stereochemistry of nucleophilic enamine species, and the iridium complex control the stereochemistry of the electrophilic iridium pi-annealing species, and thus provide full access to all four stereoisomers of the product. And another pioneering work was done by the Jung group in 2016. They reported the first example of dual metal catalysis to realize a stereodivergent annihilation of alpha hydroxy ketones. And the palladium catalyzed asymmetric anilic alkylation of benzophenone derived alpha substituted ketone imine ester provide direct access to unnatural alpha quaternary alpha amino acids. However, in reported cases, the initial selectivity was unsatisfactory, and since prochiral nucleophile is a long-standing challenge in palladium catalyzed asymmetric anilic alkylation reaction. And we designed a synergistic dual copper palladium catalytic system. And in this reaction design, a chiral copper complex was introduced to activate alpha substituted imine to form this stereocontrollable nucleophilic azomethionate. And meanwhile, a chiral palladium complex was used to generate the electrophilic pi-annealing palladium species, and producing a variety of alpha quaternary alpha amino acids in high yield with excellent initial selectivity. And the similar transformation was also reported by Jung's lab. When using glycine-derived aldehyde ester, and double anilic alkylation reaction could be performed in one-port manner, and notably, and the switching the adding sequence of the two different anilic carbonate, and both enantiomer of the product can be readily prepared. And different from the linear selectivity in palladium catalyzed asymmetric anilic alkylation reaction, and iridium complex normally provide branched selectivity. And we envisioned that merging chiral iridium complex and the chiral copper complex would provide an efficient access to alpha amino acids bearing two contiguous quaternary and tertiary stereocenter. And in this reaction, the chiral copper complex control the stereochemistry of a nucleophile, while iridium complex controls the stereochemistry of the electrophile. Thus, all four stereoisomers of the product could be predictably prepared with four different sets of catalyst combinations. And with our developed the copper iridium dual catalytic system, we realized an efficient total synthesis of this small amino acid bearing contiguous tertiary stereocenters. This is a plant growth regulator isolated from mushroom. And to be noted, previous method required at least 8 steps from optically pure starting material. And in our cases, the two contiguous tertiary stereocenter could be readily constructed in a single step from readily available starting material. And the target molecule was obtained in 3 steps in high yield with excellent stereoselectivity. And only one quantum purification was needed. And in our developed dual metal catalytic system, and this pre-activated linear anilic carbonate need to be used as a linear precursor. And in view of atom and step economy, and the branched anilic alcohol are better than the other three precursors. However, anilic alcohols are not suitable precursor because of the poor leaving ability of the hydroxy group in general, and the stoichiometric amount of Lewis acid or bronzed acid must be added to enhancing the leaving ability of hydroxy group. However, those additives are not suitable in our cases. Stoichiometric amount of transient metal Lewis acid would interfere the formation of the copper in it, while stoichiometric amount of bronzed acid would decompose the imine ester and also the iridium complex, and therefore the choice of activator is critical to this reaction design. And fortunately, we found triacylborane is the best activator to enable this reaction. And here is the proposed mechanism based on the experiment result and the DFT calculations. And the coordination of triacylborane with anilic alcohol and facilitate oxidative addition to form metal pi anilic species, along with the formation of the conjugate base. And the conjugate base help to form copper metallated isomers in it. And no additional base was needed in this reaction. And then the two catalytic cycles merged together through nucleophilic attack of the copper inlet to the electrophilic metal pi anilic species, and producing linear or branched anilation products and regenerate both catalysts. And considering there is a typical aza-anilic structure in the branched anilation product, we reasoned that increasing the steric congestion could provide the driving force for the following aza-couple rearrangement. And indeed, with the bulky alpha substituted aldehyde ester, cascade anilation aza-couple rearrangement occurred smoothly and followed by acidic hydrolysis, affording chiral homoanilic amines with perfect chiral transfer. And the imine group in the anilation product is a potential electrophilic site. And if there is another potential nucleophilic site, such as the indole group, then a further intramolecular cyclization would occur to afford indole-fused heterocycles. And with the two indole anilic carbonate as anilic precursor, we developed a dual copper iridium catalyzed cascade anilation and isopictet specular cyclization reaction, and affording a highly functionalized tetrahydrogamma carbonins. And this carbonin is a valuable core structure in many bioactive natural products and pharmaceuticals. And the first step is a stereodivergent anilation step, and enabled by dual copper and iridium catalyst. And the second step is a spontaneous and stereospecific cyclization, and to form 1,4,6 products. And therefore, in this annulation, and the two carbon-carbon bond was formed with the generation of 3 stereogenetic centers, and 4 different 1,4,6 stereoisomers could be predictably obtained. As we know, 1,3 dipole cyclization reactions are well known for the construction of 5 or 6-membered nitrogen heterocycles, while 3+2 or 3+3 reaction model. And however, a 3+4 reaction model for 7-member ring remains a challenge, and probably due to the disfavored entropic penalty and transannular interactions. And at the beginning, our design is very simple, and just moving the anilic carbonate group from indole 2 position to 4 position, and maybe 7-membered as a pine ring could be formed through 3+4 reaction model. When we're using 4-indole anilic carbonate as a precursor, and the first step and copper iridium catalyzed annihilation occurred smoothly in a stereodivergent manner, and both stereocenters could be readily controlled as before. And this is the ligand for copper, and this is ligand for the iridium complex. And however, no further annihilation was observed. And in order to enhance the electrophilicity of imine moiety, and 0.5 equivalent of zinc triphenate was added with 2 equivalent of the corresponding aldehyde. And the annihilation did occur to deliver 696 cyclooctet in stereospecific manner. And fortunately, the cis isomer can be easily epimerized into trans isomer and acidic conditions. And therefore, in this sequential stereodivergent annihilation and PS cyclization and followed by epimerization, and all 8 stereoisomer of the indole fused azopine heterocycles could be predictably achieved. And the dual copper iridium catalytic system was further utilized for the preparation of gamma butyryl lactones, and we're using this vinyl ethylene carbonate as the reactant, and all 4 stereoisomer of lactones bearing 2 contiguous stereocenters could be readily achieved. And this is the first example of azomethionate serving as a 2-atom unit for annihilation reaction, and the active iridium pi anilic species was isolated and characterized, and several control experiments were conducted to understand the mechanism and the stereochemistry of this cascade reaction. And due to time limitation, I will not mention the details. Okay, next, I would like to talk about stereodivergent Rene catalysis. And as we know, Rene catalysis can rapidly construct complex molecules from simple and readily available starting material. And since no intermediate isolation or purification, Rene catalysis is featured with stable economy and environmental friendliness. And the borohydrogen reaction has been regarded as an efficient method for the synthesis of various chiroamines derived from readily available alcohols. And in general, this reaction includes 3 steps: and oxidative dehydrogenation, and intermediate reaction, and the last step, reductive hydrogenation. And the borohydrogen reactions do not need stoichiometric amount of oxidant and reductant, and is a redox neutral reaction. Although borohydrogen reactions have been well developed, and there are very few examples of merging asymmetric borohydrogen reaction with asymmetric carbon-carbon bond forming reactions. And in 2013, with acaro-borohydrogen catalyst and caro-secondary amine catalyst, Rodriguez group reported the coupling of organocatalyzed asymmetric macroaddition reaction with borohydrogen reactions. And several years later, with acaro-borohydrogen catalyst and caro transient metal catalyst, Didier group developed the Rene catalyzed asymmetric cascade borohydrogen reaction and macroaddition reactions. And in these 2 examples, and the primary anilic alcohol were employed as the substrate, and the acaro-borohydrogen catalyst and promote the first and the third step in a redox neutral manner. And the initial determinant step is the second step in macroaddition reaction. If primary alcohol was replaced with secondary anilic alcohol, and a chiral borohydrogen catalyst was replaced with chiral one, then both the second and the third step could be initial determinant step, and thus making this cascade reaction in stereodivergent manner. And here is our design. And initially, the racemic secondary anilic alcohol was oxidized into alpha beta unsaturated ketone by chiral borohydrogen catalyst with the formation of metal hydride species. Then the enone intermediate react with the stereocontrollable copper azomethionate and affording the macroadduct chiral ketone. And subsequently, the carbonyl group in the ketone intermediate was reduced by chiral metal hydride to deliver the final product and bearing 1,4 quaternary tertiary steel centers. And for this reaction design, the first challenge is chemoselectivity, because the metal hydride could reduce the carbon-carbon double bond in alpha beta unsaturated ketones, or the imine moiety in the ketone imine ester. And another challenge is whether the initial formed chiral center will affect the formation of the second chiral center. And to make a long story short, and this reaction design was successfully realized through a dual copper ruthenium renate catalytic system. And in this reaction, and the chiral copper complex, and this is ligand for copper, and the chiral copper complex controls the initial formed chiral center, and the chiral iridium complex, ruthenium complex, controls the second chiral center. And thus, and all 4 steel isomers of the final product could be prepared with 4 different sets of catalyst combinations. And gram scale reactions could be conducted and even with the reduced catalyst loading. And the control experiment revealed that the kinetic resolution of racemic anilic alcohol was occurred in these dual metal catalyzed cascade reactions. And the deuterated anilic alcohol was employed in this reaction, and almost the same deuterium ratio was observed in the product. And this experiment indicated that this cascade reaction underwent a typical borrowing hydrogen and return hydrogen pathway. And encouraged by this promising result for the construction of 1,4 quaternary tertiary steel center, we wondered whether a renate catalytic system could be further utilized for the construction of alpha amino acid containing 1,4 tertiary steel center. And it is more challenging since alpha tertiary steel center next to the ester or the amide group is easily epumerized under basic conditions. And through careful optimization, we found that the potassium phosphonate can suppress the undesired epumerization, and the best chiral ligand for copper complex is a ferrocene-based chiral ligand with 2 phenyl group on the oxygen ring, and the different substrate need a different ruthenium complex. And for ketone imine ester, and both cis and trans product need a Rusi complex as the redox catalyst. And for ketone imine amide, and cis product require this ruthenium complex as redox catalyst. And this complex is coordinated by 2 different chiral ligands. And while trans product need the Rusi complex, and as before, and all 4 steel isomers of the product could be obtained with 4 different sets of chiral copper and chiral ruthenium catalyst combinations. And these piperidine derivatives containing 1,4 tertiary steel center is a kind of histamine H1 receptor antagonist. And a significant different biological activity between cis and trans isomers were reported. And due to the technical limitation, and the optical active steel isomers were not prepared at that time. And with the development of the copper ruthenium rennet catalytic system, a stereo divergent formal synthesis of this antagonist was performed. And the gram scale of cis and trans 4A were performed initially. And the following 6th step and then to carolactam 14, trans and cis 14, which are the key intermediate to the target molecules. Okay, now is the summary of my talk today. And in 2011, we found that the methylated isomethionine could be used as a stereo-controllable nucleophile in asymmetric microaddition reactions. And based on this finding, and with the strategy of synergistic catalysis and rennet catalysis, we developed several dual metal catalytic systems such as copper palladium, copper iridium, and copper ruthenium for stereodivergent synthesis of various alpha amino acids and heterocycles. And we believe there is extensive room for the development of dual catalysis to solve the issues of reactivity, chemoselectivity, and stereoselectivity encountered in single catalytic system. And finally, I wish to give my thanks to my collaborators for their kind help and suggestions, and also thanks to my students for their hard work. Also, thanks to the funding support from National Natural Science Foundation of China and the Ministry of Science and Technology. And finally, thanks for your kind attention.
Okay, thank you, Professor Chunjang Wang, for the wonderful presentation. So it was amazing that you guys can demonstrate forming multiple stereogenetic centers in a single part operation. Okay, now we have a few questions from the audience. So the first question can be, so we saw some example of switching between silver and copper in today's seminar. So the question is that whether you can generate silver azomethane ylide over copper azomethane ylide. Is it? I think it's that question. Can you understand?
Okay.
So in the first part of your presentation, you show many examples of copper azomethane ylide. So
yes,
can you compare and over these?
You mean compare the azomethane ylide?
With the silver versus copper.
Silver or copper? You mean the different metal precursor?
Right.
Okay. Actually, and for the azomethane ylide, normally it is a typical 1,3 dipoles for 1,3 dipole cyclotron reaction, and normally the most general metal precursor is silver or the copper salt. And however, for when methylated azomethane ylide using as a nucleophile, and in our cases, and also in the other work reported by Professor Zhang and also Professor Wei Zhi, and in their works, when we all of us found that copper metal source is the best precursor for the metal native azomethane ylide as the nucleophile. We should use in the copper metal source as a precursor. Yes.
Okay, so the next question is from Dr. Nakasuka. So he's wondering, so hydrogen borrowing reactions are relatively well established. So can you re-emphasize the importance of ruthenium in one of your projects?
Okay. I will show the slides in the, okay. Okay, this is the general pathway for the boron-hydrogen reactions. And actually, the many metal compounds can be used in these boron-hydrogen reactions. And in our cases, and as you can see, the previous work from the two French groups, they're using the ruthenium or iron air-chiral boron-hydrogen catalyst. And in our case, when we test this project, we test many boron-hydrogen catalysts, such as ruthenium or rhodium and iridium complex for the transfer hydrogenations. And however, and the best one is the ruthenium complex, and this is a complex and reported by a Chinese group. And also in the last project, and we need to using the modified. And this is the Rusi complex reported by Japanese group. And we also modify the ruthenium complex. And in these two projects, and the ruthenium complex compared with the iridium or rhodium, and the reactivity is much better than other boron-hydrogen catalyst. And
okay, thank you. Also, another question from Dr. Nakasuka is that can you kind of differentiate? It's a bit difficult question. So, can you differentiate between ligand control and then dual metal like palladium iridium metal control? So so it's a bit complicated system to us. So how you manage the ligand control and then dual metal control, including palladium and iridium?
Palladium and iridium, the metal control.
Yeah.
And I think maybe he want to know about the radius negativity of the reaction between the palladium or iridium, the different metal complex.
Yes, yeah. Can you go back to the slide?
I will go back to, okay. Okay, this is the copper and palladium catalytic system. And in this reaction, and the nucleophile attack to the terminal position of this pi annealing palladium species. And when we replace the palladium complex with the iridium complex, and in this case, and the radius selectivity is different. This is a branched selectivity.
I see.
And the main reason for the branched selectivity of iridium complex is there is no simple answer to this question. And I think I will try to answer this question with the metal complex. I think maybe I can show here. And as you can see, this is the copper iridium complex. And why iridium complex in this reaction exhibit a branch selectivity, and it can be explained by the electron effect and the steric effect. As you can see, and this is the iridium pi annealing species, and the iridium and carbon 1 bond, and the iridium carbon 3 bond. The iridium carbon 3 bond are longer, the bond distance is longer than iridium carbon 1 bond.
Mhm.
And therefore, the steric congestion and prevent the attack from the terminal position. And also, we collaborated with Professor Yanfeng Dang in Tianjin University, and they also did DFT calculations on this complex, especially on the positive charge distribution on these 3 carbon atoms. And this carbon 3 is much electrophilic, thus for the iridium catalytic annealing activation and provide the different radioselectivity, that is branched selectivity. Okay.
Okay, thank you. So in your previous question, so you explained the importance of copper in the formation of azomethyl halide. So another question from the audience is that, is copper compatible to all other metals in general? Then do you see any issue in the compatibility with the copper? So I think it is the question.
Okay, I will return to the slides. Okay, in this slide, I show the metal dated as method ended, and the nucleophilicity was enhanced with better stereoselectivity control. And actually, for 1,3 dipole cyclodieldrin reactions, and many metal complex can be used, and many metal precursor can be used, such as copper, silver, and zinc, and nickel. And however, and just as I mentioned before, and when we using metal dated as method ended as the nucleophile, and the best metal species and is the copper. And I cannot explain, give explanation to this. And I think maybe the copper can coordinate well with nitrogen and oxygen atom, and to form this rigid species. And until now, and actually, when we test some project, we also try to using silver as the metal precursor, and sometimes and the reactivity or the stereoselectivity control is less satisfactory. And but I think because silver is also a gold metal precursor for 1,3 dipole cyclodieldrin reactions, I think it should be formed the similar rigid species. And
right.
So we think I think if the audience invested the similar nucleophilicity of the azomethyl halide, maybe copper and silver can still be screened. And okay.
I see. Thank you so much. So I'm not sure whether I delivered those questions from the audience very well, but if it's not clear, probably the Professor Wang will be happy to answer your question by email. So okay, with that, I would like to thank Professor Wang for the wonderful presentation once again. Okay. All right, so I think I can close the webinar by thanking all 3 speakers, as well as all the authors involved in the special issue for dual catalysis. I'm sure you all convinced by the power of dual catalysis for making multiple stereogenic centers and very complicated compounds. And then please join me thanking all 3 speakers today. And please visit SYNTHESIS website to find out more about dual catalysis special issue and all other special issues going on in synthesis. Okay, then.
Yeah, okay, thank you. Thank you, Jung. Yeah, thank you for being the chair of today's seminar, and also thank the three speakers for their wonderful lectures about dual catalysis, and it shows really great potential to synthesize very complicated compounds via synergistic strategy. So I believe, yeah, all of the audience will learn something from their lectures, and thanks again. And also thank you for all the attendees for your time. Yeah, and as I mentioned at the beginning, yeah, the seminar will be recorded and the link will send to you, yeah, if you sign up. Okay, so thank you, and
Okay, thank
yeah,
you.
have a nice day.
Thank you.
Thank you so much.
Thank you. Bye-bye.
Thank you.
Bye.
Bye-bye.
Bye. Thank you all for coming, and then we are gonna close the session soon.
Yeah.
Thank you.
Yeah. Thank you. Bye-bye.
Bye.